For centuries, the cosmos was perceived as a realm of profound silence, an empty canvas where light painted stars, but no sound could ever journey. This notion, rooted in our earthly understanding of sound, requiring a medium to travel, left the vast stretches of space seemingly devoid of acoustic resonance. Yet modern astrophysics challenges this very silence, revealing a universe that, in its own extraordinary way, hums and vibrates with an incredible symphony of energies. The paradox begins with how we define sound. On Earth, it's the vibration of air molecules reaching our ears. In the vacuum of space, air, of course, is absent, but the universe is not truly empty. It's filled with plasma, gas, dust, and dark matter, mediums through which energy can propagate, albeit not as traditional sound waves. These cosmic echoes manifest as pressure fluctuations or ripples in spacetime itself. To hear these cosmic vibrations, we must abandon our reliance on human ears. Instead, scientists employ sophisticated instruments, telescopes that detect everything from radio waves to gamma rays, and observatories designed to measure the faintest ripples in the fabric of spacetime. These are our new ears, extending our perception far beyond the narrow band of audible frequencies. The true challenge then becomes translation. The gravitational waves from merging black holes don't make a boom in space. Instead, they are minuscule distortions of distance that require incredibly sensitive detectors to record. Once captured as data, these patterns can be converted into audible frequencies, a process known as sonification, allowing us to genuinely listen to the universe's unseen movements. While a conventional astronaut floating in space would experience profound silence, advanced technologies unveil a subtle, omnipresent hum emanating from the cosmos. This isn't the kind of hum you hear from a refrigerator, but rather the collective noise of countless astrophysical processes taking place across vast cosmic distances, energies that shape galaxies and stars. This redefinition of sound offers a profound new sense, unlocking secrets previously hidden in plain sight. It allows us to perceive what was once imperceptible, transforming abstract data into patterns our brains can more intuitively grasp, bridging the gap between complex physics and human understanding, bringing us closer to knowing the universe. Historically, the vacuum of space perpetuated the myth of absolute silence. But even before advanced instruments, early radio astronomy hinted at cosmic noise. Today, we understand that cosmic sound is about different forms of energy propagation: gravitational, electromagnetic, and particle-based, all carrying information about the universe's dynamic processes. Imagine light as a visible sound that needs no medium, traveling unimpeded. Cosmic sound isn't quite as straightforward, requiring a medium like plasma for pressure waves or the very fabric of spacetime for gravitational waves. It's crucial to differentiate these forms of cosmic communication from the simple atmospheric pressure waves we directly hear. The process of sonification itself is an art and a science, carefully mapping measurable physical properties like frequency, intensity, and duration from cosmic data onto audible parameters like pitch, loudness, and rhythm. This transforms incomprehensible numerical arrays into discernible musical or rhythmic patterns, enabling auditory analysis. Thus, when we speak of listening to the universe's deep hum, we are not imagining a traditional orchestra playing in the void. Instead, we are engaging with a multisensory scientific endeavor, using technology to reveal the universe's true vibrant nature, translating its energetic movements into a novel form of perception, allowing us to truly experience its symphony. The common misconception that space is utterly silent stems from our earthbound experience. Sound, as a wave of pressure, needs a medium like air or water to propagate. In the near-perfect vacuum between stars and galaxies, there simply aren't enough molecules for such a wave to form, and travel traditionally from source to ear. Hollywood often depicts dramatic explosions and roaring spacecraft in space films. While exciting, these are artistic liberties. In reality, an exploding star would be visually spectacular but acoustically mute to any proximate human observer without specialized equipment capable of converting other forms of energy into sound. Our reliance on pressure waves for hearing means that sound, as we know it, effectively stops at Earth's atmosphere. Beyond this protective bubble, the sound waves generated by phenomena like solar flares or planetary movements dissipate instantly without a medium to carry their vibrations. Even though cosmic events like collisions or dramatic celestial discharges release immense energy, that energy manifests as bursts of light, gravitational waves, or streams of charged particles, not as audible pressure waves. It's a different kind of energetic transfer we must learn to detect. So despite the immense power of events like a gamma-ray burst, a nearby listener, if one could survive, would experience only flashes of blinding light, not deafening noise. The absence of traditional sound is a fundamental property of the cosmic vacuum, profoundly different from any environment on Earth. This illusion of absence extends to our own solar system. While Voyager probes hum with their instruments and stars glow with incredible fury, the space between them is a silent highway for light and particles, utterly devoid of audible frequencies we could perceive directly. The closest thing to sound waves in space are plasma waves, which are oscillations of charged particles in a magnetized plasma. While these propagate, their frequencies are typically far too low for human hearing, measured in millihertz, requiring specialized receivers and translation. Therefore, the cosmic silence isn't a lack of phenomena, but a lack of conventional sound propagation. It forces us to reconsider what hearing means, stretching our sensory definition to encompass detecting and interpreting every form of energy that voyages across the void. The profound silence of space is, paradoxically, what makes its sounds so fascinating. It highlights the ingenuity of human science to overcome sensory limitations, transforming invisible forces into something relatable, allowing us to perceive the universe not just visually, but through new, interpreted auditory dimensions. Ultimately, the absence we perceive is an absence of our asterisk kind of sound. The cosmos is teeming with vibrations and energy transfers. The challenge and thrill lie in transcending our biological limits to decode these signals, transforming the illusion of silence into a vibrant tapestry of cosmic rhythms and echoes. While traditional sound travels as pressure waves through a medium, space, though largely a vacuum, is not truly empty. It's permeated by fields and particles. Thus, vibrations across the void refer to entirely different phenomena. Fluctuations in gravitational fields, oscillations of plasma, or electromagnetic emissions interpreted as sound. One of the most groundbreaking vibrations detected are gravitational waves, ripples in spacetime itself, caused by the most violent cosmic events. These aren't sound waves in any conventional sense, but they distort space and time, a measurable vibration that can be sonified into an audible signal. Even though electromagnetic waves, light, radio waves, X-rays don't carry sound, their varying frequencies and intensities can be translated. A radio telescope detecting fluctuating radio emissions from a pulsar, for instance, can render these variations into clicks or hums, providing an auditory representation of the source. Plasma, the fourth state of matter, is abundant in space. In regions like planetary magnetospheres or nebulae, charged particles can oscillate and create plasma waves. Although these waves are typically at extremely low frequencies, below human hearing, sensitive instruments can detect and convert them to audible whooshes or whistles. The universe itself can be seen as a vibrating tapestry of interconnected fields and forces. From the grand scale of galactic superclusters to the quantum realm, there are constant energetic interactions that, while silent to our direct ears, continuously provide data for scientists to listen to. This new sense allows us to perceive what was once invisible and inaudible. By mapping physical properties of cosmic phenomena to sounds, we gain an entirely different dimension for analysis, detecting patterns and rhythms that might be missed in visual or data representations alone. The very formation of stars and planets generates a host of vibrations. As protostellar clouds collapse, they create shockwaves. As planetary systems form, their nascent atmospheres churn with energetic activity, all leaving signatures that can be detected and interpreted. Events like solar flares or coronal mass ejections, which violently expel charged particles from the sun, generate ripples in the solar wind that can travel across the solar system. Detectors on probes can pick up these energetic pulses and translate them into distinct sounds. This innovative approach ultimately redefines our understanding of cosmic communication. It moves beyond just seeing the universe to actively perceiving its dynamic, underlying energetic processes, essentially giving us a synthetic auditory experience of the cosmos's deepest motions. By embracing these vibrations across the void, we gain a richer, more profound appreciation for the universe's complexity. It transforms the perceived silence into a symphony of data, inviting us to tune into a cosmic orchestra playing on timescales and wavelengths far beyond our natural reach. The key to hearing the inaudible universe lies in sonification, the process of mapping data points to sound parameters. This isn't just about making cool noises. It's a powerful analytical tool that allows scientists to perceive patterns, anomalies, and rhythms in complex datasets that might be missed through visual inspection alone. Imagine vast arrays of numbers representing temperatures, pressures, or electromagnetic frequencies from distant cosmic phenomena. Sonification takes these numbers and translates them into corresponding pitches, volumes, and timbres, turning raw data into an auditory landscape. One of the simplest examples is translating fluctuating radio signals from pulsars. The precise, rhythmic pulses of electromagnetic energy are converted directly into clicks or beeps, effectively allowing us to listen to these cosmic lighthouses ticking across the galaxy. NASA frequently uses sonification for educational outreach and scientific discovery. For example, the fluctuating magnetic field lines around Jupiter can be turned into haunting whoosh sounds, giving us a feel for the planet's powerful magnetosphere. The chirp of merging black holes, detected by LIGO, is a quintessential example of sonification. Gravitational wave signals, which are minuscule spacetime distortions, are sped up and shifted in frequency to become an audible rising tone, allowing us to hear the most violent events in the universe. This translation isn't arbitrary. There are established methods and algorithms. Scientists strive to maintain the integrity of the data, ensuring that the auditory representation accurately reflects the underlying physical parameters. It's a scientific method, not just artistic interpretation. Different types of cosmic data yield distinct sounds. The slow, rhythmic oscillations of a giant star might translate to a deep hum, while fast, energetic bursts might become sharp, percussive sounds, forming a diversified cosmic soundscape. Data sonification is also crucial for accessibility, offering a way for visually impaired individuals to engage with astronomical findings. It opens up the wonders of the cosmos to everyone, regardless of their sensory abilities. From the faint whispers of distant exoplanetary atmospheres to the powerful roars of supernovas, every energetic signature in the cosmos holds the potential for auditory translation. This means we're not just looking at the universe, we're beginning to orally explore it. The field of astronomical sonification is constantly evolving, with new techniques and algorithms emerging. It's transforming our interaction with cosmic data, turning otherwise silent numerical inputs into an emerging symphony of cosmic revelations, a true frontier in sensory astronomy. The Big Bang wasn't a silent visual expansion. It was a universe undergoing extreme acoustic oscillations. In the immediate aftermath, the cosmos was a dense, hot plasma where sound waves or pressure waves could actually propagate. Imagine a universe so compact, it literally rang like a bell. For the first 380,000 years after the Big Bang, the universe was opaque, a fog of ionized particles. Photons were constantly scattering off free electrons, preventing light from traveling far. But within this plasma, density variations could create pressure waves that traveled faster than light today. These early universe sound waves weren't like sound in air. They were actual density fluctuations in the primordial soup, causing regions to become slightly hotter or cooler, denser or less dense. Think of them as cosmic ripples spreading through the early universe's fluid-like state. These acoustic oscillations are incredibly important because they imprinted a signature on the universe that we can still detect today. They are directly responsible for the initial distribution of matter, laying the groundwork for the large-scale structures we observe, like galaxies and galaxy clusters. The sound here is conceptual, but the physics is real, a medium through which pressure waves could travel. The early universe, being a hot plasma, acted as akin to a giant, resonant liquid, allowing these primordial sound waves to propagate and interact. These sound waves would have reflected and interfered with each other, similar to how waves behave in a contained space. This created a specific pattern of peaks and troughs in the density of the plasma, which later translated into variations in the cosmic microwave background. When the universe cooled sufficiently for electrons and protons to combine and form neutral atoms, the fog lifted, and the sound waves largely stopped propagating as the medium changed. This pivotal moment left an indelible imprint. Cosmologists use complex simulations to play back these early universe acoustics. By inputting the known physics, they can recreate the soundscape of the nascent cosmos, understanding how these primeval vibrations shaped everything we see today. The scale of these primordial sound waves was astronomical. They were not localized, they filled the entire universe, creating a universal tune that directly influenced where matter would eventually clump and where voids would form. So the Big Bang wasn't silent. It was a symphony of pressure waves, a truly cosmic roar that laid the foundation for every star, galaxy, and structure in existence. We just needed to learn how to decipher its ancient, fossilized echoes. The cosmic microwave background, or CMB, isn't just the afterglow of the Big Bang. It's effectively the universe's oldest photograph and its first hum. It's the residual radiation from when the universe cooled enough to become transparent, about 380,000 years after its birth. Before this moment, the universe was a superheated, opaque plasma. Photons were constantly interacting with free electrons. When temperatures dropped, electrons combined with protons to form neutral hydrogen atoms, allowing photons to travel freely. This liberation of light is what we detect as the CMB. These photons, which have traveled billions of years to reach us, carry the imprint of those very early acoustic oscillations. The minute temperature variations we see in the CMB correspond to the peaks and troughs of those primordial sound waves. The CMB is almost perfectly uniform, but those tiny variations are incredibly significant. They are the seeds of all future structures, the slight density differences that gravity would later amplify to form galaxies and clusters. The hum comes from the fact that these variations appear at distinct scales, much like different notes in a chord. These specific scales relate directly to the wavelengths of the sound waves that were propagating in the early universe just before the CMB was formed. By analyzing the power spectrum of the CMB, essentially how strong these temperature variations are at different scales, cosmologists can precisely determine crucial parameters of the universe, such as its age, composition, and geometry. This is akin to reading the universe's blueprint. The first, most prominent peak in the CMB power spectrum corresponds to the largest sound waves that could oscillate during the universe's opaque phase. This peak acts as a standard cosmological ruler, providing fundamental insights into the cosmos. Modern detectors like the Planck satellite have mapped the CMB with unprecedented precision, unveiling an astonishing level of detail in this cosmic hum. Every nuanced fluctuation tells a story about the conditions of the early universe. This ancient hum isn't just a relic, it's a living echo that continues to shape galactic evolution. The distribution of matter, dictated by the CMB's slight variations, directly influences how galaxies clump and structures form over billions of years. Listening to the cosmic microwave background allows us to tune into the universe's first, most fundamental sound. It's a silent, permeating hum that acts as a profound testament to the Big Bang's acoustic legacy, a universal background noise providing clues to everything. Acoustic oscillations in the early universe were crucial. Imagine the primordial plasma not as a static soup, but as a dynamic fluid where density waves propagated, similar to how sound waves travel through water. These were the true ripples in the primordial plasma. Before 380,000 years post-Big Bang, the universe was hot and dense enough for electrons and protons to remain largely separate, forming a charged plasma. This plasma acted as a medium capable of supporting pressure waves, much like atmospheric air. As gravity tried to pull matter inward, radiation pressure from photons pushed it back out, creating a continuous cycle of compression and rarefaction. This push-and-pull mechanism generated acoustic waves, causing the plasma to oscillate. These oscillations weren't uniform, they occurred at various wavelengths. The largest waves had enough time to complete roughly one full oscillation before the universe cooled and became transparent, leaving a distinct imprint. The exact musical notes or scales of these oscillations are visible as the peaks and troughs in the angular power spectrum of the cosmic microwave background. Each peak corresponds to a specific type of acoustic oscillation that imprinted itself on the departing light. The first acoustic peak in the CMB spectrum is particularly important. It tells us about the geometry of the universe, confirming that our cosmos is flat, meaning light travels in straight lines on large scales. Subsequent peaks reveal more complex details, indicating the relative densities of dark matter, baryonic matter, normal matter, and dark energy in the early universe. These overtones in the cosmic sound reveal its precise composition. Picture a cosmic drum vibrating after the Big Bang. The sound waves reverberated within this expanding drum, leaving subtle density differences that acted as gravitational seeds. Over billions of years, these seeds would grow into galaxies and galaxy clusters. The precision with which we can measure these acoustic oscillations is a triumph of modern cosmology. It confirms the Big Bang model and provides precise numbers for otherwise fundamental cosmic parameters, strengthening our understanding of the universe's origins. These are the universe's oldest fossils, not bones, but patterns of density variations. By studying these ripples in the primordial plasma, we can rewind time to the very early moments of creation, truly listening to the Big Bang's original, shaping vibrations. Approximately 380,000 years after the Big Bang, a pivotal event occurred, the epoch of recombination. Before this, the universe was an opaque, scorching plasma, but as it expanded and cooled, free electrons finally joined with atomic nuclei, primarily protons, to form neutral hydrogen and helium atoms. This formation of neutral atoms had a profound acoustic consequence. It effectively silenced the universe in terms of traditional sound waves. Free photons, previously scattering off incessant free electrons, were now liberated to travel unimpeded. With electrons bound to nuclei, the medium that supported the primordial sound waves largely disappeared. The cosmic plasma, which acted as a fluid, became a gas of neutral atoms, a far less efficient medium for pressure waves to propagate across vast scales. Imagine a drum that suddenly loses its skin. The vibrations cease. Similarly, the universe's drum skin, the free electron plasma, vanished. This moment fixed the pattern of acoustic oscillations into the cosmic microwave background, preserving their imprint for us to detect today. This epoch is also called decoupling because photons decoupled from matter. The light we now see as the CMB is the light that was released at this precise moment, carrying the frozen audio recording of the universe's final primordial sound waves. The universe literally cleared up. Before recombination, observing the universe was like trying to see through a dense fog. After recombination, the fog lifted, revealing the newly formed, quiescent, and transparent cosmos. While gravitational waves and plasma waves would still propagate after this epoch, the large-scale acoustic pressure waves that shaped the overall initial mass distribution largely ceased. The universe became acoustically quieter in a broad, cosmological sense. This transition wasn't instantaneous, it was a process, but its effects were profound. It marked the end of the early universe's hot, dense, and acoustically active phase, paving the way for the formation of stars and galaxies in a cooler, quieter cosmos. The epoch of recombination provides a critical snapshot for cosmologists. By studying the precise details of the CMB, which originates from this moment, we can infer the conditions of the universe just as it transformed from opaque to transparent. In essence, the universe let out its last great primordial roar during recombination, and then its acoustic waves faded into a background hum. This quieting event allowed the universe to begin its long, silent journey of structure formation. While traditional sound waves can't travel through a vacuum, gravitational waves are an entirely different phenomenon. Predicted by Einstein, these are ripples in the very fabric of spacetime itself, caused by accelerating massive objects like cosmic cataclysms. Imagine stretching a rubber sheet and placing heavy balls on it. They create dips. Now imagine those balls suddenly accelerating or colliding. They would send ripples across the sheet. Gravitational waves are precisely that, but on the cosmic scale, and the sheet is spacetime. Detection of gravitational waves by LIGO in 2015 revolutionized astronomy. It opened a brand new window to the universe, allowing us to listen to events previously utterly silent and invisible to electromagnetic telescopes. These detections usher in an era of multi-messenger astronomy, where we combine data from gravitational waves with traditional light observations, radio, X-ray, visible, to get a more complete picture of cosmic events. When two black holes spiral inward and merge, they emit a characteristic gravitational wave chirp. As they get closer, they spin faster, generating higher frequency waves, which scientists translate into an audible rising pitch. Gravitational waves are incredibly faint by the time they reach Earth. The distortion they cause is infinitesimally small, less than the width of a proton over detection distances of kilometers. This makes their detection an outstanding technical achievement. Unlike light, gravitational waves are not scattered or absorbed by matter. They pass through everything unimpeded, giving us an unadulterated view into the universe's most violent and obscured cataclysms, like the interiors of supernovae. Beyond black hole mergers, gravitational wave observatories aim to detect signals from colliding neutron stars, exploding massive stars, supernovae, and even the stochastic background of gravitational waves left over from the Big Bang itself. Future gravitational wave detectors, both ground-based and space-based like LISA, will extend our listening capabilities to even lower frequencies, effectively tuning into different channels of the cosmic gravitational symphony. Gravitational waves are truly a new form of listening, a vibrational sense that reveals the universe's most extreme energetic events. They are the ultimate cosmic deep hum, allowing us to perceive the universe not just by its light, but by its titanic shudders. Among the most spectacular sounds interpreted from gravitational waves are those originating from the collision of massive black holes. These are not literally sound waves, but violent shudders in spacetime itself, detected by observatories like LIGO and Virgo. As two black holes orbit each other, they generate gravitational waves carrying immense energy away from the system. As they approach merger, their orbital speed increases dramatically, causing the frequency and amplitude of these waves to rise, creating a characteristic chirp. The chirp, detected by LIGO for the first time in 2015, was the sound of spacetime itself being warped by objects 29 and 36 times the mass of our Sun, merging into a single, even larger black hole. It was a cosmic event of unimaginable power. The rising pitch of the chirp signifies the increasing gravitational wave frequency as the black holes accelerate. The sudden cessation of the chirp marks the moment of merger, when the new, single black hole briefly rings down before settling. These mergers are among the most energetic events in the universe, releasing more power in a fraction of a second than all the stars in the observable universe combined. This energy is carried away as pure gravitational radiation. By studying these chirps, scientists can determine the masses of the merging black holes, their spins, and even test Einstein's theory of general relativity in extreme gravitational environments, providing invaluable insights into fundamental physics. The ability to convert these gravitational waveforms into audible sounds allows us to intuitively grasp the dynamics of such violent events. The rising pitch evokes the accelerating cosmic dance, offering a profound sense of scale and power. Each new black hole merger detection adds to our growing catalog of cosmic chirps, revealing a population of these extreme objects far more active than previously imagined, continuously reshaping our understanding of galaxy evolution. The noises from colliding black holes are far more than just audible curiosities. They are direct windows into stellar death, the formation of supermassive black holes, and the very structure of spacetime itself, providing critical data for cosmology. These chirps are the universe's most extreme gravitational bellows, allowing us to listen to the very fabric of reality being violently twisted and stretched by the cosmos's most enigmatic and powerful giants. While black hole mergers produce powerful chirps, neutron-star collisions offer a different, multifaceted cosmic sound. These mergers are even more complex, involving fantastically dense matter and producing both gravitational waves and electromagnetic radiation. Neutron stars are the collapsed cores of massive stars, packing more mass than our Sun into a sphere barely the size of a city. When two of these superdense objects spiral towards each other, spacetime warps dramatically, creating gravitational waves that LIGO can detect. The first observed neutron-star merger, GW170817, in 2017, was a monumental discovery. Not only did it produce a distinct gravitational wave chirp, similar to black holes, but much faster and shorter, it also emitted a gamma-ray burst and optical light. The gravitational wave signal from neutron-star collisions is unique. Due to their extended structure and interaction, they have more complex waveforms than black holes, providing information about the equation of state of nuclear matter itself. These mergers are cosmic alchemists. They are believed to be the primary cosmic factories for producing heavy elements like gold, platinum, and uranium through a process called nucleosynthesis, scattering these rare elements across the universe. The sound of these events often includes a rapid-fire series of kicks or chimes in the gravitational waveform, reflecting the incredibly complex dynamics of two superdense objects tearing each other apart. A critical aspect is the post-merger signal, the intense jiggle of the remnant object, which might temporarily form a hypermassive neutron star before collapsing to a black hole, creates a hum at extremely high frequencies, offering clues to nuclear physics. This simultaneous detection of gravitational waves and light allows us to precisely pinpoint the location of the event in the sky. This convergence of seeing and hearing radically enhances our understanding of the universe. Studying neutron star kisses provides profound insights into the behavior of matter under the most extreme conditions imaginable, densities where a teaspoon would weigh billions of tons. It's the ultimate cosmic laboratory. These celestial kisses are loud events in the gravitational spectrum, translating into unique chirps and high-frequency jiggles. They are a symphony of dense matter, revealing secrets not just of cosmic alchemy, but of the very fundamental forces holding matter together. Spacetime isn't a static backdrop. It's a dynamic fabric that can be warped and stretched by mass and energy. Massive accelerating objects, like merging black holes, literally cause this fabric to sing by generating gravitational waves. Einstein's general relativity postulates that gravity isn't a force pulling masses together, but a curvature of spacetime caused by mass and energy. The universe's song is simply this spacetime responding to dynamic changes in its curvature. When cosmic objects undergo violent accelerations, like supernovae explosions or binary star systems spiraling inwards, they create dynamic changes in this spacetime curvature. These changes propagate outwards as gravitational waves, much like ripples from a stone in a pond. The singing is extremely subtle. By the time these waves reach Earth, the distortion they cause to spacetime is incredibly small, expanding and contracting space by less than the width of an atom. Yet, instruments like LIGO are precise enough to detect it. The frequency of the gravitational waves determines the pitch of this spacetime song. Rapidly accelerating objects produce higher frequencies, higher pitches, while slower, more massive movements produce lower frequencies, deeper hums. The loudest songs detected so far are the high-frequency chirps from merging black holes and neutron stars. But the universe likely hums with a much deeper, lower-frequency background song from countless less energetic events. Space-based gravitational wave observatories, like the planned LISA mission, are designed to capture these incredibly low-frequency gravitational waves. These will reveal new cosmic sources, like supermassive black hole mergers in distant galaxies. Beyond individual events, there might be a constant, faint, gravitational wave background, a lingering echo from the very early universe, or the superposition of all gravitational wave events throughout cosmic history. This would be the universe's true bass note. This concept of warping spacetime profoundly changes our perception. It's not just a stage for cosmic drama, it's an active participant, resonating and responding to the most powerful events, continuously shaping and being shaped. The fabric of spacetime is a silent musician, playing out the gravitational symphony of the cosmos. By learning to listen to these subtle shudders, we are gaining an intimate understanding of the universe's ultimate orchestra and its cosmic refrains. The birth of stars is a symphony of collapsing gas and dust, a process that, while silent in a vacuum, emits powerful, directional flows of matter and energy known as protostellar jets. These jets are essentially the birth cries of nascent suns. Stars aren't born with a gentle fizzle. A protostar, still gathering mass, violently expels excess angular momentum through these colossal jets. These jets can extend light years into space, punching through surrounding gas and dust. These jets slam into the surrounding interstellar medium, creating energetic shockwaves. While not sound waves in the traditional sense, these collisions generate intense X-ray and radio emissions, which can be translated into powerful roars when sonified. The sound of these jets is often characterized by high-energy bursts and continuous, powerful hums when converted. The sheer force involved ensures a strong, energetic signature that can be detected across vast distances. Herbig-Haro objects are spectacular visual manifestations of these protostellar jets interacting with nebular gas. They glow brightly as the shocked gas heats up, revealing the path of these cosmic birth cries. The wobble of a forming star and its accretion disk, as it slings material into these jets, generates subtle ripples in the surrounding gas, which are effectively pressure waves on a grand cosmic scale. Scientists study the velocity and direction of these jets through Doppler shifts in their light. This data, when sonified, can reveal the changing forces at play during a star's tumultuous birth, from gentle inflows to violent outflows. These jets are not just cosmic fireworks. They are crucial to star formation, helping to shed excess angular momentum, allowing the central protostar to accrete more material and eventually ignite nuclear fusion. The sheer scale of these protostellar phenomena implies tremendous power. While we cannot hear them directly, our instruments reveal a universe resounding with the powerful, shaping forces of creation, manifested as these energetic cries. So the birth cries of stars are not audible wails, but titanic energetic expulsions. They are the universe's way of marking the inception of a new sun, providing a powerful, translated sound of creation itself echoing across the void. Supernovae, the cataclysmic explosions of massive stars, are among the most spectacular and energetic events in the universe. While they explode in a vacuum, their serenades are not silent. They manifest as intense bursts of light, neutrinos, and crucially, powerful shockwaves. A core collapse supernova begins when a star's core runs out of nuclear fuel, collapses, and then rebounds, sending a powerful shockwave outwards. This wave rips through the star, expelling its outer layers into space at incredible speeds. This shockwave is akin to a cosmic sonic boom. While it's not truly sound-carrying in a vacuum, its passage heats and compresses the surrounding interstellar gas, creating observable ripples of X-rays and radio waves that can be sonified. The translated sound of a supernova can be a sudden, percussive blast followed by a long, lingering crescendo as the remnant expands and interacts with its environment. It's a cosmic gong striking once, then resonating for millennia. The famous Crab Nebula is a supernova remnant, the expanding shell of a star that exploded in 1054 AD. Observations reveal its continuously expanding filaments, emitting different forms of light that, when sonified, create distinct auditory textures. Neutrinos, practically massless particles, are released in torrents during a supernova. These particles pass through matter almost unimpeded, carrying vital information about the core collapse. If we could sonify their arrival, it would be a sudden, dense shower of clicks. The light curve of a supernova, how its brightness changes over time, can also be sonified. A rapid rise might translate to a quick crescendo, followed by a slow, decaying hum as the light fades over months or years. Supernovae also leave behind incredible compact remnants like neutron stars or black holes. The birth of these objects generates gravitational waves, hinting at a deep, resonant rumble accompanying the stellar death. These explosions actively enrich the cosmos, scattering heavy elements formed within the star and during the explosion back into space, providing the building blocks for new stars, planets, and even life. Thus, supernovae are not silent departures, they are cosmic serenades of destruction and creation. They are the universe's ultimate fireworks, generating profound energetic aftershocks that, through sonification, we can perceive as powerful, lasting echoes. Pulsars are rapidly spinning neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As they spin, these beams sweep across space, creating precise, lighthouse-like pulses that, when detected, produce remarkably rhythmic ticks or whirs. Imagine a cosmic lighthouse blinking with astonishing regularity. The fastest known pulsars can spin hundreds of times per second, creating millisecond pulses. This extreme precision makes them nature's most accurate celestial clocks. When astronomers sonify pulsar data, the varying intensities of the radio pulses are mapped to auditory clicks or chirps. The regularity of these pulses creates a distinct, almost hypnotic rhythm, unique to each pulsar. Some pulsars emit X-ray and gamma-ray pulses as well, each contributing a different timbre to their cosmic rhythm when translated. This multi-wavelength data provides a richer, acoustic portrait of these exotic objects. The discovery of the first pulsar in 1967 initially led scientists to wonder if they had detected alien signals, given their incredible precision. It was Jocelyn Bell Burnell who recognized their astrophysical origin. Pulsars are invaluable cosmic laboratories. Their rhythmic pulses are used to test Einstein's theory of general relativity, detect gravitational waves through their arrival timing deviations, and even measure cosmic distances. The slowing down of a pulsar's rotation, a tiny reduction over time, indicates energy loss. This subtle change, when sonified over long periods, could be perceived as a gradual, almost imperceptible lowering of its rhythmic pitch. Binary pulsar systems, where two pulsars orbit each other, offer even more complex rhythms. Their orbital decay due to gravitational wave emission was the first indirect evidence for gravitational waves before direct detection by LIGO. Over 3,000 pulsars have been discovered, each with its unique rhythmic signature. They form a vast, celestial percussion section, ticking away with incredible precision across the galactic disk. Pulsar rhythms are truly the universe's ticking clocks, a silent, yet powerfully translated metronome marking out cosmic time. They are the heartbeat of collapsed stars, a constant, precise testament to the universe's powerful and predictable physics. Black holes are often perceived as silent, light-devouring abysses. However, the superheated gas spiraling into their accretion disks generates incredibly powerful X-ray and radio emissions. These black hole bellows are the energetic signatures of matter's final moments. As gas and dust fall into a black hole, they get compressed and heated to millions of degrees, radiating intense light across the electromagnetic spectrum, particularly in X-rays. This radiation is the primary source of their observable noise. The fluctuations in brightness and frequency from these accretion disks can be sonified. Rapid, irregular changes might translate into chaotic roars or crackling sounds, reflecting the turbulence of the infalling matter. Supermassive black holes, residing at the centers of most galaxies, can actively feed, drawing in vast amounts of gas and stars. This active feeding creates powerful, active galactic nuclei, AGN, which are among the loudest cosmic emitters in X-rays and radio waves. The supermassive black hole at the center of the Perseus galaxy cluster emits pressure waves every 10 million years, sending ripples through the cluster's hot gas. These are true sound waves traveling through a cosmic medium, albeit at incredibly low frequencies. When amplified and sped up by millions of times, these Perseus cluster pressure waves can be heard as a low, ominous B-flat. The actual sound generated by a black hole's bellows reaching human ears through sonification. Jet-emitting black holes, like those found in quasars, launch powerful, collimated beams of plasma at nearly the speed of light. These jets emit intense radio emission, which, when sonified, can create a continuous, powerful cosmic hiss or scream. The variable X-ray emissions from stellar mass black holes in binary systems can reveal the dynamics of their feeding. These flickering patterns, when transformed into sound, provide a unique flicker noise signature of the black hole's activity. The black hole bellows are not mere background noise. They are crucial to understanding galaxy evolution, regulating star formation, and revealing the mysterious interplay between supermassive black holes and their host galaxies. So black holes are not silent monsters. They are cosmic speakers, broadcasting the violent, energetic cacophony of consuming matter. Their bellows are the universe's loudest whispers, revealing the ultimate fate of stellar and galactic material. Galaxies are not static islands of stars. They are dynamic entities that often collide and merge. These galactic crescendos are monumental events, reshaping entire stellar populations and generating vast cosmic sound signatures that we can detect. When galaxies merge, their massive black holes eventually spiral towards each other and coalesce, generating incredibly powerful low-frequency gravitational waves. These waves are too low for current detectors, but will be prime targets for future space-based observatories. As galaxies approach, their vast gas clouds collide, creating shockwaves that trigger bursts of star formation. These starbursts are visually spectacular, emitting intense light and radio waves, which can be sonified into vibrant, energetic bursts of sound. The drag and friction between colliding gas and dust within merging galaxies create heating. This energy is radiated across the electromagnetic spectrum, contributing a broadband hiss or fuzz to the cosmic soundscape when translated. Tidal forces during a merger stretch and distort the galaxies, forming long, elegant tidal tails of stars and gas. These vast structures, some stretching hundreds of thousands of light years, trace the paths of the cosmic dance. Supermassive black holes at galactic centers also launch powerful jets during mergers as gas is funneled toward them. These jets, emitting intensely in radio frequencies, contribute a focused roar or scream to the overall symphony. Numerical simulations allow cosmologists to model these complicated mergers, mapping the density and velocity of gas. When these simulations are sonified, they reveal the complex, evolving acoustic themes of a galactic collision. The cosmic chorus from a merger changes over time. Initially, it's the large-scale gravitational pulling, then bursts of star formation, followed by the eventual roar of merging black holes. It's a multi-act cosmic opera. Observing these galactic crescendos provides vital clues about how galaxies grow and evolve, how structures form on the largest scales, and the role of supermassive black holes in shaping their cosmic neighborhoods. Galactic mergers are truly the universe's ultimate crescendos, a titanic clash that transforms the cosmic landscape. Their sonic signatures, once translated, reveal the powerful, majestic, and often violent forces that construct the universe we see. On the largest scales, the universe isn't a random scattering of galaxies. It forms a vast, interconnected network known as the cosmic web. This web consists of dense clusters of galaxies connected by long, thin filaments, separated by immense voids. The whispers originate here. These filaments are colossal structures stretching hundreds of millions of light years. They are composed of diffuse gas, dark matter, and galaxies, acting like highways along which galaxies migrate and interact. Within these filaments, large amounts of hot, diffuse gas exist, known as the warm-hot intergalactic medium, WIM. While extremely tenuous, its slight density variations can support very low-frequency acoustic-like waves. The slow gravitational infall of matter onto these filaments and into clusters generates gentle shockwaves. These are not loud booms, but gradual compression and heating, like distant, barely perceptible whispers of cosmic growth. Observations of X-ray emissions from the WIM, though challenging, can reveal these faint pressure fluctuations. When sonified, these are the universe's ultimate background ambient noise, a low, ethereal hum signifying the continuous accretion of cosmic matter. The whispers are a form of cosmic feedback. As galaxies form and grow, they release energy that can propagate through these filaments, potentially influencing star formation in distant regions of the web. Different parts of the cosmic web might have distinct tonalities based on their density and temperature. Denser regions might have slightly higher frequency whispers, while the vast, empty voids would be truly silent. Mapping these faint acoustic fluctuations within the cosmic web is a frontier of cosmology. It involves detecting incredibly spread-out energy across colossal scales, pushing the limits of our observational capabilities. Superclusters, the largest structures in the universe, also create gravitational potentials. The movement of galaxies within these structures might generate extremely low-frequency vibrations in the cosmic medium, a vast, slow, gravitational breathing. The filaments' whispers are the universe's softest sounds, revealing the subtle yet continuous processes of accretion and growth on the grandest scales. They are the background ambient noise of cosmic evolution, a testament to the universe never truly being still. Dark matter, the mysterious, invisible substance that makes up about 27% of the universe, plays a crucial role in forming cosmic structures. While we can't directly see it, its gravitational influence creates subtle echoes that might eventually be interpreted acoustically. We infer dark matter's presence through its gravitational effects on visible matter, such as the rotation curves of galaxies or the gravitational lensing of distant objects. It forms invisible halos around galaxies and permeates the cosmic web. In cosmological simulations, dark matter forms complex, intricate structures, shaping the scaffolding of the cosmic web. The movement and interactions within this dark matter framework can generate a form of subtle, long-wavelength acoustic signature. The very slight pressure waves in the ordinary matter of the early universe were influenced by the gravitational potentials of dark matter. These interactions left a signature on the CMB, which are essentially the initial echoes of dark matter's presence. If dark matter particles interact, even weakly, they could emit faint, secondary particles or radiation. While not direct sound, these emissions could be detected and sonified, acting as indirect, acoustic signatures of dark matter behavior. Hypothetical dark acoustic oscillations within certain dark matter models propose that dark matter itself might have undergone its own early universe sound wave propagation, entirely separate from baryonic matter. Detecting these potential dark sounds would require incredibly sensitive instruments, looking for minuscule temperature fluctuations or slight density variations in patterns beyond those explained by visible matter. It's a deep cosmic listening challenge. The cosmic dance of dark matter within galaxy halos or clusters could generate slow, large-scale gravitational distortions over immense timescales. These could be considered a form of extremely deep, low-frequency hum. Efforts like the search for WIMPs, weakly interacting massive particles, or axions, hypothetical dark matter candidates, are attempts to find these subtle echo-generating interactions. Any breakthrough here could provide direct, acoustic evidence. The dark matter echoes aren't audible sounds, but their gravitational imprints and potential subtle interactions are a form of silent data. By searching for these acoustic signatures, we might finally unravel the deepest, most enigmatic mystery of the cosmos. Dark energy, the mysterious force driving the accelerated expansion of the universe, has a profound influence on the cosmic tempo. It's not a sound source itself, but it dictates the speed and dynamics of the universe's grand narrative. Before dark energy's dominance, the universe's expansion was decelerating due to gravity. But now, it's speeding up, like a runaway note in a cosmic symphony accelerating beyond expectation, forever changing the universe's ultimate future. This acceleration means that distant galaxies are receding from us at an ever-increasing rate. Their light is becoming more redshifted, and eventually, many faint and far-off galaxies will recede beyond our observable horizon entirely. If we were to sonify the collective hum of the universe, dark energy's influence would mean this hum is constantly dropping in pitch over cosmic time, as distances between objects expand faster and gravitational interactions weaken. Dark energy might also suppress the growth of large-scale structures like galaxy clusters. As the universe expands ever faster, gravity struggles to pull matter together, potentially leading to a quieter, more isolated cosmic future. The physical nature of dark energy is still unknown. It could be a constant energy density of space itself, Einstein's cosmological constant, or a dynamic field. Its properties profoundly impact the cosmic soundscape's evolution. The influence of dark energy means that the universe's expansion will become increasingly dominant over gravitational forces. This signals a transition to a cold and lonely future for galaxies, further isolating them from each other. By studying the accelerating expansion and its effects on galaxy distribution, cosmologists are trying to precisely measure dark energy's equation of state. This essentially means understanding its role as the universe's ultimate musical conductor. Even though dark energy doesn't produce sound, its accelerating effect on the cosmos influences how all other cosmic sounds propagate and evolve over time. It stretches wavelengths, dilutes signals, and ultimately shapes what we can hear and see from the distant past. Dark energy's influence is therefore not a sound, but a profound, accelerating rhythm and tempo that defines the universe's ultimate fate. It is the unseen orchestral leader, dictating the grand pace of the cosmos. Some of the universe's most profound sounds are generated by processes that aren't directly observable by sight. These phantom sounds are often created by exotic or immense phenomena requiring indirect detection and careful interpretation. Ultra-high energy cosmic rays, fragments of atomic nuclei traveling at near light speed, arrive from mysterious, distant sources. While they don't make sound, their passage through detectors creates showers of secondary particles that can be sonified into sharp clicks. The theoretical ocean of neutrinos permeating space is another source of phantom sounds. While elusive, if we could detect their individual interactions, they would create a constant, low-level hiss, revealing the deep, unseen flow of particle creation. The cosmic neutrino background, a relic analogous to the CMB but for neutrinos, carries information about the very early universe. Detecting this faint, ancient signal would be like tuning into a deeply buried, primordial whisper. The hypothesized existence of cosmic strings, theoretical one-dimensional defects in spacetime, could generate unique gravitational wave signatures, perhaps a continuous buzz or hum from their oscillations across the universe. Dark matter annihilation, if it occurs, could produce gamma rays or other particles that might be detectable. These would represent phantom sounds of dark matter destroying itself, providing critical clues to its nature. The elusive dark energy could have internal dynamics or fluctuations if it's a dynamic field rather than a constant. These hypothetical fluctuations could generate ultra-low frequency, phantom sounds that warp spacetime on immense scales. The sound of the quantum vacuum, a theoretical sea of virtual particles constantly popping in and out of existence, is not directly measurable, but it's the conceptual foundation of all other physical phenomena, the ultimate silent hum. These phantom sounds are the realm of theoretical physics and future observatories, pushing the boundaries of what we can possibly detect and interpret from the universe's most hidden processes. The phantom sounds of the universe are the unheard melodies of its most profound mysteries. While they lie beyond our current direct detection, the pursuit of these hidden orchestra leaders drives the next generation of cosmic discovery. Exoplanets, planets orbiting stars beyond our sun, are now counted in the thousands. While we can't directly hear their winds or storms, their atmospheres leave unique detectable sonic signatures encoded in the light they transmit or reflect. The composition of an exoplanet's atmosphere, its temperature and pressure determine how light interacts with it. By analyzing changes in starlight as it passes through the atmosphere, scientists can infer the presence of gases. Different atmospheric gases absorb or emit light at specific wavelengths. These absorption and emission fingerprints are unique. By mapping these spectral patterns to auditory frequencies, we can hear the chemical makeup of alien worlds. The sound generated would be a unique spectral chorus. Water vapor might hum at one frequency, carbon dioxide at another, creating a distinct atmospheric tune for each alien world. Powerful winds on gas giants could create measurable pressure fluctuations within their vast atmospheres. While not audible to us, these dynamic movements could influence the planet's gravitational field, detectable as subtle long-term variations. Extreme atmospheric phenomena, like lightning storms on a vast scale, could generate radio bursts that travel through space. These bursts, once detected and sonified, could be translated into crackling or popping sounds of alien weather. Changes in an exoplanet's brightness as clouds move across its face or as it experiences large-scale climate shifts can be monitored. When sonified, these varying light patterns could reveal the dynamic rhythms of an alien climate cycle. Future telescopes like the James Webb Space Telescope are providing exquisite detail on exoplanetary atmospheres, allowing for increasingly precise listening to these alien worlds, chemical compositions, and thermal conditions. Biosignatures, gases that are likely produced by life, like oxygen or methane, would generate very specific spectral notes. Their detection and subsequent sonification would be the most profound sound an exoplanet could utter. The atmospheres of exoplanets are vast cosmic canvases painted by unique physical and chemical processes. By translating the data from these atmospheres into sound, we transform distant points of light into worlds with their own distinct, translated winds and atmospheric melodies. Listening for life in the universe means looking for biosignatures, specific gases or features in a planet's atmosphere that are highly indicative of biological processes. These are the universe's ultimate sound bites of alien existence. For example, the presence of both oxygen and methane in a planet's atmosphere, particularly in significant, long-term quantities, is highly suggestive of life. Both gases are unstable and require continuous replenishment, often by living organisms. While we can't literally hear alien organisms, the light passing through a habitable exoplanet's atmosphere will carry the spectral notes of these biosignatures. Each element or compound absorbs light at a precise wavelength. When these spectral absorption patterns are sonified, the presence and abundance of biosignature gases would translate into particular musical pitches or timbres, instantly alerting scientists to a potentially inhabited world. The search for biosignatures extends beyond gas composition. Features like specific light polarization from photosynthetic organisms on a planet's surface could also provide a detectable signal, a subtle, reflected hum of photosynthesis. The presence of water, while not a direct biosignature, is crucial for life as we know it. Its spectral signature would be a key component of any potential habitable world's acoustic profile, acting as a foundational note. Future telescopes are being designed specifically for biosignature detection, pushing the limits of atmospheric characterization. These ambitious missions aim to directly listen for the faint chemical whispers of life. The challenges are immense. Planetary atmospheres are often shrouded in clouds, and biosignatures can be mimicked by geological processes. Distinguishing true signs of life requires a suite of robust detections and careful interdisciplinary study. If we ever detect definitive biosignatures, their sonified patterns would be the most extraordinary sound ever received. It would be the universe finally whispering back a profound answer to our deepest question: are we alone? Listening for life through biosignatures transforms distant points of light into potential living worlds with their own unique songs. It's the universe's ultimate musical quest, seeking the specific notes that signify the grand concert of existence beyond Earth. The search for extraterrestrial intelligence, or SETI, is fundamentally a quest to listen for artificial signals rather than natural cosmic phenomena. It's about tuning into SETI's symphony. Radio signals that betray the presence of technological civilizations. Radio telescopes are the primary instruments for SETI. Their ability to pick up incredibly faint radio waves at specific frequencies makes them ideal for detecting potential communication signals from distant civilizations, unhindered by intervening gas and dust. The waterhole is a particularly important frequency range for SETI, between the hydrogen and hydroxyl emission lines. These are ubiquitous cosmic frequencies with low background noise, making them ideal potential communication channels for intelligent life. If a signal were detected, it wouldn't likely be direct audio. Instead, it would be a modulated radio wave, a series of pulses, frequencies, or patterns. Sonifying these patterns would allow us to hear logical sequences, like a repeating prime number series. The WOWW signal, a famous anomalous radio burst detected in 1977, remains unexplained. While not confirmed, its distinct, strong, and narrowband nature sparked hope, a tantalizing whisper that hinted at something artificial. More recent efforts use fast radio bursts, FRBs, as targets, mysterious, extremely powerful, but brief radio emissions from cosmological distances. While currently attributed to natural phenomena, some patterns could conceivably be artificial. SETI doesn't only listen for direct messages. It also looks for technosignatures, any detectable indicator of technology, such as waste heat from alien megastructures or unusual light patterns from large-scale engineering. Computational power allows SETI to analyze vast amounts of data, searching for incredibly subtle, non-random patterns embedded within cosmic noise. It's like sifting through immense static to find a faint, coded melody. The potential reception of an intelligent signal would transform humanity's understanding of its place in the cosmos. It would be the universe's ultimate musical offering, a direct communication from another mind. SETI's symphony is a quest rooted in profound hope and persistent listening. It's the most deliberate attempt to hear beyond the natural background hum of the universe, seeking the intelligent notes that might signify we are not alone. The whispers of habitability are not direct sounds, but a combination of atmospheric and planetary characteristics that suggest a world could host liquid water and, potentially, life. These are chemical and physical notes that compose a life-friendly tune. The presence of liquid water is paramount. Its spectral signature in an exoplanet's atmosphere and evidence of oceans on its surface are strong indicators. This would be translated into a distinct, foundational hum in a planet's profile. A rocky terrestrial composition is another key note. While gas giants exist in habitable zones, a solid surface is essential for life as we know it, allowing for complex chemistry and stable environments. The habitable zone, or Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. A planet residing here produces a warm, inviting chord of environmental conditions. A stable star is also crucial. Stars prone to frequent Powerful flares might strip away atmospheres or irradiate a planet, making it less habitable. A calm, long-lived star provides a steady, consistent beat for life to evolve. The presence of a protective magnetic field, like Earth's, can shield a planet from harmful stellar wind and radiation, preserving its atmosphere and surface conditions. This adds a crucial shielding note to the habitability symphony. Atmospheric composition plays a vital role. A suitable amount of greenhouse gases, like carbon dioxide, can help regulate temperature and keep a planet warm enough for liquid water, creating a balanced thermal soundscape. The age of a planet and its star also matters. Life often takes billions of years to evolve to complexity, so a mature, stable system offers a long, sustained composition period for intricate life to emerge. The presence of a gas giant in the outer system, like Jupiter, can act as a celestial sweeper, gravitationally deflecting comets and asteroids away from inner planets, ensuring a quieter, safer habitat for developing life. The whispers of habitability are composite sounds, a harmony of many planetary characteristics. They are the chemical and physical notes that, when combined, create the possibility for the grandest symphony of all. The emergence of life. Beyond the familiar optical spectrum, the universe hums with energy across a vast range of wavelengths undetectable by the human eye. Radio telescopes, in particular, are our ultimate listeners, allowing us to tap into this unseen realm. From the flickering of pulsars to the immense jets of active galaxies, many of the universe's most energetic phenomena emit predominantly in radio frequencies. These are otherwise silent to optical instruments, making radio astronomy crucial to a fuller soundscape. Radio waves are much longer than visible light waves and can penetrate vast clouds of dust and gas that obscure optical views. This means radio telescopes can see, and thus listen, to phenomena hidden deep within nebulae or galactic centers. Detection of the cosmic microwave background, CMB, was a landmark discovery made with a radio antenna. It was the universe's first, deepest hum, picked up as a persistent, faint static from every direction. Radio telescopes can pick up faint, low-frequency atmospheric sounds from planets like Jupiter, caused by plasma waves in their magnetospheres interacting with the solar wind. These are often translated into eerie whooshes or whistles. The chirps from merging black holes and neutron stars, though primarily gravitational waves, also often have electromagnetic counterparts that produce radio flashes, which radio telescopes can detect, confirming the event. The hydrogen line at 21 cm wavelength is particularly important for radio astronomy. It allows astronomers to map the distribution and movement of neutral hydrogen gas throughout galaxies, essentially listening to the raw material of star formation. Global networks of radio telescopes, like the Very Long Baseline Array, operate as a single, enormous virtual dish, achieving astronomical resolution. This allows for incredibly detailed acoustic mapping of distant cosmic sources. The Square Kilometre Array, SCAR, currently under construction, will be the largest radio telescope ever built. It promises unprecedented listening capabilities, delving deeper into cosmic evolution and potentially detecting faint signals from exoplanets. Radio telescopes are redefining our perception of the cosmos. They are our ears for the universe's most subtle and most violent whispers, tuning into invisible frequencies to reveal a cosmos constantly singing in a range beyond our sight. Interferometry is a powerful technique that combines signals from multiple telescopes, effectively creating a single, much larger virtual telescope. This enhances sensitivity and resolution, allowing for exquisite harmony in cosmic sensing. In radio interferometry, signals from widely separated dishes are combined, exploiting the wave nature of radio signals. When the wave fronts from a source arrive at different antennas, they create interference patterns that, when analyzed, yield ultra-high-resolution images. This is akin to superimposing the sound waves from multiple microphones to isolate a specific voice in a crowded room. The combined data reveals details unseen by any single instrument alone, bringing cosmic details into sharp focus. The Event Horizon Telescope (EHT), which famously imaged the supermassive black hole at the center of M87, used Earth-sized interferometry. Dishes across the globe worked in unison to synthesize an image of unparalleled detail. Optical interferometry also exists, using multiple visible light telescopes to achieve much sharper images than single telescopes. This can reveal finer details in exoplanetary atmospheres or stellar surfaces, providing new visual notes. Resolving power achieved by interferometry allows us to essentially zoom in on cosmic sources with incredible precision, enabling us to differentiate individual structural elements and sources of emission, like distinct voices in a choir. For gravitational wave astronomy, the LIGO and Virgo detectors form an interferometer network. The precise timing of a gravitational wave arriving at each detector allows triangulating the source location, refining the auditory pinpointing. Interferometry opens up new vistas of cosmic sound, from mapping the fine gas structures within merging galaxies to resolving the emission regions of active galactic nuclei. Each new detail adds to the symphony. Space-based interferometers like LISA will achieve even larger baselines, enabling the detection of lower-frequency gravitational waves from events like the mergers of supermassive black holes. This extends our listening range considerably. Interferometry's harmony is about leveraging the wave nature of signals. By combining cosmic senses across immense distances, it allows us to piece together a richer, more finely tuned acoustic portrait of the universe than ever before. Data sonification is the artistic and scientific practice of turning numerical data into sound. It transforms the universe's vast, silent data streams into audible forms, allowing human perception to grasp complex patterns through a new sensory channel. This isn't just about entertainment. Scientists use sonification to identify anomalies, trends, and periodicities in datasets that might be too subtle or complex to discern purely through visual graphs or tables. Imagine mapping the brightness fluctuations of a variable star to pitch, or the intensity of a cosmic ray burst to volume. Different parameters can be mapped to different aspects of sound: timbre, duration, spatialization. NASA has pioneered sonification, creating audible interpretations of everything from the solar wind impacting planetary magnetospheres to the expansion of supernova remnants. The universe now has a dynamic soundtrack. A famous example is the sonification of black hole mergers, where the increasing frequency of gravitational waves is mapped to a rising pitch, producing the iconic chirp that revolutionized astronomy. Another application is in exploring exoplanet atmospheres. Different chemical elements detected through spectroscopy can be assigned unique musical notes or instrument sounds, creating a chemical melody for each alien world. Data sonification makes complex astronomical datasets accessible to a wider audience, including the visually impaired. It transforms abstract scientific concepts into intuitively understandable sensory experiences. The choice of mapping parameters in sonification is critical. It involves careful consideration to ensure scientific accuracy while producing an aesthetically pleasing and informative auditory experience, bridging art and science. Future advances in sonification may involve real-time auditory displays in control rooms, allowing astronomers to hear subtle changes in cosmic phenomena as they unfold, providing prompt insights into dynamic events. Data sonification is truly about turning numbers into notes, transforming the cosmos from a silent visual spectacle into a vibrant, multisensory experience. It allows us to interpret the universe's language in a whole new dimension. Our human brains are remarkable cosmic interpreters, constantly making sense of incomplete or abstract information. When presented with sonified cosmic data, our brains spontaneously seek patterns, rhythms, and meanings, even in the silence. Neuroscientists find that auditory processing in the brain is incredibly adept at recognizing subtle changes in pitch, tempo, and timbre. Sonification leverages this innate human capability to uncover hidden relationships in complex datasets. The aha moment of discovery can often come from hearing something unexpected in sonified data. A sudden spike in pitch or an unusual rhythm can instantly draw attention to a cosmic anomaly that might have been overlooked visually. Our brains are wired for narrative. Sonification helps construct a narrative from cosmic events. The rising pitch of a black hole merger tells a clear story of accelerating approach and collision, a concept far more gripping than a numerical plot. Different people perceive and interpret sonified data uniquely. This diversity of perception can sometimes lead to new insights, as different brains pick up on different patterns or nuances in the cosmic soundscapes. The intuitive nature of sound allows us to quickly assess vast amounts of information. A complex stellar oscillation might be represented by a rich, multi-layered chord that instantly conveys its complexity, rather than requiring analysis of many individual data points. Human perception also involves emotional response. The deep, ominous hum of a black hole or the violent crackle of a pulsar can evoke a visceral connection to the immense forces at play in the universe, deepening our understanding. Training our brains to interpret these new cosmic languages is an ongoing process. It expands our cognitive toolkit, moving humanity beyond merely observing the universe to deeply interacting with its fundamental rhythms. This re-engagement with our auditory sense for cosmic discovery is a testament to human adaptability. Our brains, ancient as they are still evolving to interpret the vast, new sensory universe unfolding before us. Ultimately, our brains are the universe's ultimate cosmic interpreters. By transforming the silent universe into a symphony of data, we enable our inner cosmos to resonate with the outer cosmos, creating a profound, empathetic understanding of our place within it. The universe's soundscape is not static, it's constantly evolving. From the initial roar of the Big Bang to the current era of accelerating expansion, the cosmic hum is gradually fading, its individual melodies stretching and diminishing over colossal timescales. In the early universe, the acoustic oscillations were vibrant and powerful, thanks to the dense plasma acting as an efficient medium. The cosmic microwave background captures this peak performance of the cosmic orchestra. As the universe expanded, the density of matter and energy decreased. This dilution causes all forms of cosmic sound, from plasma waves to gravitational wave frequencies, to redshift and stretch, lowering their perceived pitch and intensity. We are living in an era where the universe's expansion is accelerating due to dark energy. This means that distant cosmic sounds are receding from us faster than ever before, becoming fainter and redshifted more rapidly. The chirps from merging black holes will become rarer in the distant future as fewer galaxy mergers occur. The grand galactic crescendos will eventually subside as the universe becomes more isolated. As stars exhaust their fuel, the birth cries of protostellar jets will dwindle, and supernova serenades will become less frequent. The stellar component of the cosmic soundscape will slowly fade out over trillions of years. The last stars will eventually die out. The long, rhythmic ticking of pulsars will slowly wind down. The black holes will continue to merge, creating late gravitational wave chirps, but even these will become rare as the universe ages. The distant future holds a universe dominated by black holes and cold, dead remnants. Its soundscape will be a near-total silence, broken only by exceptionally rare gravitational waves from black hole evaporation or distant, isolated mergers. This fading hum provides a poignant perspective on cosmic time. The universe had its peak acoustic period, and we are fortunate to be alive in an era where enough of its past echoes and present symphonies are still discernible. The universe's hum will eventually become a whisper, then ultimately a silence of vast distances and cold, dark remnants. But for now, we can still tune in, listening to its fading symphony and revel in the profound, dynamic music of its cosmic evolution.